So this is a little bit jumping out of order because I usually don't bother bringing this up until chapter 6. But again, like I said, the beginning of chapter 6 will be next week, Thursday, okay? A couple lectures from now. The first thing we get into once we wrap up proteins. It will make it onto quiz 1, at least a little bit, so worth introducing now, okay? Internal energy, capital U is what we will use. You may, again, when looking at other resources, you'll get capital E. So this is one that there's two popular notations. Okay? What is total internal energy of a system made up of? There's 2 parts, and we've already said them, so I know you know them. Kinetic and potential, love it. Okay? The kinetic energy, so temperatures, again, are a relative measure of this, sort of a metric for us to understand kinetic energy. Okay? Average kinetic energy of the particles in a system. We can identify that with temperature. Potential energy, we said for our sake, what we're interested in is intra. So what's intramolecular bonding mean versus inter? What's the difference between these two? Yes. Perfect. Intra was within the molecule itself, that single molecule, so that long string of proteins that we'll eventually start talking about, the backbone bonds in it, the bonds within that single protein are my intra bonds, and then inter is sort of what is it doing with other stuff. And in this case, we generally will call it interactions as opposed to bonding, simply because it's going to be non-covalent stuff. Okay, so proteins are going to interact with other proteins rather than bond with them through hydrogen bonds, van der Waals, sterics, hydrophobic interactions, stuff like that. Okay. So here we have, which from this little picture here, there's 2 atoms attached by a squiggle that is supposed to be a bond. I didn't draw this. So of those 3 choices, translational, rotational, and vibrational, which one is the kinetic energy piece? Translational, movement through space, things are moving, kinetic energy, this little v here is meant to be velocity. Okay. Rotational and vibrational are potential energy modes, okay? So before I actually break a bond, I can put energy in and get bond rotation and bond vibration, maybe some bond stretching, and those are all sort of things happening in terms of potential energy before I would actually maybe break it apart. If people remember the example from last Thursday, I drew like a double bond on the board and said like maybe you could bend it out of plane, or cis-trans were 2 different energy levels of one double bond. Okay, so change in that delta term for no matter what it is, you can always write it as final minus initial, okay? Or once we actually start looking at chemical reactions, write it as products minus reactants, okay? And that always works. Final minus initial, products minus reactants, if that's, a way you want to just memorize it, that's the best way to always write the subtraction for your delta. Okay, so it's going to be change in kinetic energy plus change in potential energy. What is absolute zero? Who wants to explain it? Yes.
It's always described in Kelvin, so it's basically the point at which there's no movement of any there's no energy in that system, there's no movement whatsoever.
There's no what kind of energy?
Potential, or kinetic energy.
Kinetic energy, okay. Right? Perfect. So it is the absence of kinetic energy, okay? When you're at absolute zero, since temperature is a relative measure of kinetic energy, there's no kinetic energy. Everything stops moving. It would be as if everything could become a solid. It's not real, but wouldn't it be great? Wouldn't it make all of our math easy if everything was at absolute zero? But yes, it is the absence of kinetic energy, okay? Everything stops moving, but you still have bonds. And in fact, like I said, things would have to become solid, so maybe even bonds that wouldn't typically form would be there. What does isothermal mean? So absolute zero, I have 0 Kelvin. There is no temperature to speak of, kinetic energy's gone. And what's isothermal?
Like the heat, heat's the same.
Let's not use heat, because heat is gonna mean something really specific later. Temperature, okay? So iso, same, thermal, temperature is not changing, okay? And again, this is sort of from a macro perspective, when I look at it, the overall temperature of what's going on doesn't change. This reaction happened at room temp. Doesn't mean bond rearrangements didn't happen, doesn't mean bond enthalpy didn't change, but net temperature didn't have to change from a macro view, okay? Let's see. So, if temperature is constant, is what's going on with the delta kinetic energy, that delta KE term? It's dropping out, right? So if I'm thinking about isothermal, like the human body, we usually are gonna treat it like an isothermal system. We're hanging out at 37 C or 310 Kelvin, right? We're at body temp. The other common temperature we'll use throughout class is room temp, or 298 Kelvin or 25 C is what we'll use most often. So what that means then is any changes in internal energy, changes in delta U are coming exclusively from the potential energy term, the changes in bond rearrangement, the enthalpy term. Okay? So sort of what we'll eventually see is delta PE is going to be equal to delta H. The potential energy and enthalpy are sort of interchangeable when we start talking about the things we care about, which are going to be isothermal systems. And I said, you know, we'll revisit it later. Temp and heat, they're not the same. You can have heat transfer without a temp change. You can have a temp change without heat transfer, and we'll talk about how to do that when we get in chapter 6. But one of the other things that should maybe cue you off is just units, right? So what are the units of temp? What are the units of heat? Joules, okay? It's a type of energy, joules. Heat is going to be in joules. Temp is going to be in Kelvin. They're not the same thing. Temp is a relative, like a metric for evaluating kinetic energy. It is not in itself, it's not kinetic energy exactly. Temperature is a unique thing. It's a way we need to describe our kinetic energy. And again, these are not the same, and I think minding your units is a good way to remind yourself of that. Okay. Here's another combustion example, okay, except we have glucose now. Okay, so C6H12O6 is glucose molecule. Okay. When we add oxygen, we can have combustion to form water and CO2, and we have delta U equals negative 2801 kilojoules per mole. Okay. So is this a favorable reaction? Why? There's a negative. Great. Could this happen at one temperature? Could I put this in some sort of containment where I can control temperature and force it to combust but not let temperature change? I can. We can do it. We have all sorts of type of calorimeters where we can stop pressure from changing, stop volume from changing, stop, put the control on it. And so what that means is like we could think of this potentially exclusively in the potential energy changes and the enthalpy changes. So again, a negative delta U is going to be, here's two new words for you, exothermic, okay? An exothermic reaction, exo, exit, heat energy exits, heat out, enthalpy out, potential energy out, however you wanna get all those words aligned in your mind, okay? If it's a positive change in internal energy, positive delta U, we would say that this is an endothermic reaction, okay? En, endothermic, enter, heat enters, heat goes in, however you like to memorize it. My favorite is when we finally get to chapter 11 and we do redox. I couldn't remember the redox, like mnemonics, the Leo says grr or whatever they are. I had to have students like remind me what the mnemonics were. What's a mnemonic for like kingdom, phylum? What was that from bio? I don't remember that either. Right? I mean, does anyone remember one of those? I don't. I'm a fan of mnemonics. Okay, so some of you know them. But yeah, I mean, if you have a cool mnemonic to remember anything from this class, some fun thermo ones, that's taking suggestion. All right, so this is the combustion of glucose is an exothermic reaction. It releases 2,801 kilojoules of energy for every mole of reactants, okay? This is a mole of glucose. 1 mole of glucose is reactant. And like I said, right now, I just wanna present this to you because we're gonna show some energy curves, we're gonna maybe like look at some drawings, talk about bond energy rearrangements, and I think it's just good to talk about which part of internal energy the bond rearrangements are, and how to think about all the sign convention rather than waiting a couple weeks to introduce it. I do care a lot about you being comfortable looking at different types of energy diagrams. Like I said, some type of energy being on Y and something else being on X, and there might be different versions. So here's one you've probably seen, right? And this one's labeled just very generally as energy, okay? But of course, we know that it's talking about potential energy, enthalpy, because it's showing delta H here. Okay, so we have reactants, and we have products. Delta H is negative, why? Because products minus reactants, products is lower, okay? And the other thing to think about is just everything, this is favorable, this wants to happen, however you like to think about that, is simply because lowest energy is best case. That's where everything wants to be, right? In this case, course of reaction, later in the book, we'll call this reaction coordinate, progress, reaction progress, any of that might be on the x-axis, I don't care so much. And we don't really talk about catalysis in this class in too much detail, a little bit and much later. But what this is showing here is that these reactants sitting on the table aren't going to spontaneously form into product necessarily without some sort of initial input of energy. And one of the examples that we will eventually do is maybe like a heat pack or a cold pack, right? So like an ice pack sitting there, you know, you have to break it. You have to like shake it up and let everything mix before it starts to feel cold or it starts to release heat if you have a hot pack or whatever. So there's still this initial input, but once I get it going, it continues to heat or continues to feel cold. The reaction proceeds spontaneously afterward. And then for an endothermic reaction, it's gonna look something like this. And I will just tell you now, we could draw something similar for, we could put Gibbs on the Y, you know, we'll see similar looking curves later on for other stuff.